Hello, welcome to the poster. My name is Keenan. I'm the last author. So let's go ahead and go through. Main gist is that DLBCL, most common blood cancer, P53 mutations, obviously bad. What we're finding is that when treated with CAR T in the relapse or refractory stage, we are finding that P53 again is sort of rearing its ugly head. So figure one's kind of just saying, all right, so in pre-diagnosis, what does a P53 set of patients look like if they have mutations versus not mutations, right? Versus no mutations. So quick gene ontology tells us stuff that like we kind of already assume, know. We know that immune regulation is one of these, cell death as well, and all the other bad stuff. Looking here, it's kind of a nice overview. Wanted to highlight something that has also been kind of showing up in the CAR T conversations, that it's TNF RSFB1 or 110B. Sorry, it's gonna be a hard one, I guess. So looking at this is a death receptor. This is on the tops of cells, and DERPA 2020 in blood found that if that's gone, on average, that makes CAR Ts not work as well, at least in vitro, right? So P53 with regular, just in, this is de novo cases right here. Cool thing that we found, I mean, maybe unsurprising, but using deconvolution, if we take a look at the CD8 T cell presence, if that deconvolution is not there, you end up in this curve right here as a P53 patient. Equally, if you are one standard deviation below the average expression of TNSFRB1, or sorry, 10B, my bad. And again, same relationship right here. If you do not have a get it deconvolution CD8 signature, this is how you're going to end up right here, at least in the ZooMone 2020 data set that we're utilizing in this case. So taking a look at these two, if we pair these up, we can see genes in this case right here that are down in both. Double highlighted blue, double significant. These are also kind of summarized right here if you want to pause and get that. Not that it's too crazy. Then we got some genes that are high in both. But it's the genes that are low in both that we're a little more looking at. A lot of those genes, again, so this is sort of a mirror of the analysis we just did, except now we're doing it with immune deconvolution values. The data set we're using has 418 patients. I believe 61 of them have P53 mutation, and somewhere around, what was it? It was like 35, no, 40, yeah, a little more than that even. 51 have low TNSF or SF10B. Gonna be a long night. Now, what you're looking at is a very fun, cool way to show the deconvolution XY. What factors are lost when both of these things are present? You are losing CD8s, you are losing M0s, you're losing your gamma deltas, you are losing a lot of M1s. You are strangely, hey, data's the data. Neutrophils came along for the ride. They're not usually something that you lose in DLBCL, and it's a good thing. Okay, we're taking a look at some more established signatures from the Stout lab. If I take a look at two of these right here, and if I'm looking at gene values for P53 genes, that like what's their average Z-score for each of those genes in the signature for interferon and STAT respectively, like we're looking at right here, we see that P53 looking pretty bad, right? Now, same thing is going to happen over here when you have that low death receptor. And right here, we're just going to take a look at some of our characteristic immune genes. What we're going to do here is that we have the Zoo data set, and then we have this TCGA data set, a little lower power, only like about 51 cases. But it's a good DNA RNA integrated set. Seeing this, you can tell low CD8, low CD28, low CD8A, low IFNG each time, and then just matching things up again. We see this relationship twice. Nothing novel there, just confirming what we know. Okay, taking a look. How do we want to target this? Okay, so if we have an issue with P53 before, we have always turned to a drug called Idasnutlin, or at least MDM2 inhibitors, because MDM2 is an inhibitor of P53. We have something unique now, Eprenetapopt. This is a P53 reactivator. It was the plenary talk on the last day of last year's ASH. What we're hypothesizing is that if you bring these back, you can bring back the death receptor and you can make things more attractive for CAR T. Now, if we look at these as single agents, Eprenetapopt in white, Idasnutlin in black, we see that they have some decent efficacy across the board as single agents. Not too bad, right? These are both in micromolars right here, but I mean, not what you wouldn't expect for your standard drug. Also, we do see probably wouldn't to be too far from the obvious, which is if you're wild type, this is going to get a lot easier. If you're a nonsense mutation, there's no coming back in some cases. That's Carpus 422 for you. Now, good news is that when you put these together, it's pretty aggressive. Not bad, right? I think in the long run, we would really like to redo these experiments in a lot more cell lines and continue seeing this relationship before we get too certain. But at the same time, synergy is synergy, and it's exciting to see right here. We also got some single treatments with a lot of replicates coming through. Things worked out pretty well as far as relative cell viability. So, fun times. This is one that sort of summarizes things right here. This is an integrative analysis of 3 different data sets. Left to right is, do you lose? Oh, I can see myself in this camera. I'm going the wrong way. Do you lose genes? Do you gain genes when you have P53? That is your x-axis. Your y-axis is from DERPA 2022 or 2020. How important are you to the CAR T's toxicity? Last one, Louise, 2021. There was another author on that actually. It changed sometimes. If you inhibit MDM2, what happens to the gene? Does it rise up in green and come back from the dead, or is it lower, purple? Now, there's one on here that really fits the criteria for all 3. That is TNFR-SF10B. Obviously, fat is a little more important, quite a bit more important for CAR T, but it's not coming back in this case. And it's actually gained when you have P53 mutations. That's why I think that this investigation has a lot of merit to say, okay, can we bring this back? We see pretty quickly that you can bring this back with either drug, but in combination, it really shines through. You can even see some of the actin on here is a little bit lower, and it's still going to shine through in a lot of cases in that combination of both drugs. Now, as we continue, obviously, I've kind of ignored the DNA alterations up to this point, sorry. If we're looking at a quick similarity matrix, if this is low TNF, TNFR-SF1B, P53 is its first little partner. From there on, this is descending and showing who it is associated with if you just 1-0 that value into a low set of patients for that -1 standard deviation. And we see, again, not everything falls in the same category, similar to when we see P53 mutations show up. Right here, what I was kind of hoping to look at and look for is that if we take the zoo data set that we're looking with, which is de novo DLBCL, about 418, we compare those expression splits of P53 to those in the Chuval data set, which is RR DLBCL, relapsed refractory. I wanted to see what stuff rises and what stuff goes down further, I should say, and rises further, I should say. This is a difference between the 2 data sets. What we see down here in a lot of cases, see that one of these genes that is going even further down after relapse refractory in these P53 patients is our death receptor. So again, reiterating a lot of results that we've seen in the past, but for the first time, hopefully Bridget and I taking another step to say we have sort of cornered this pathway a little better. And hopefully we've taken a small step towards precision medicine and DLBCL and hopefully informed things a little bit on the in vitro level. And we'd be excited to see the next step. Thank you so much for stopping by.